Hello, everybody. If you are here to join us for the Ask the Moldflow Experts webinar, How Thin is Too Thin, you're in the right place. So sit back and relax. We're going to wait a couple of minutes as people filter into the webinar here. So we'll start in a couple of minutes. Okay, I think it's a good time to go ahead and get started. Some people will still continue to filter in here, but I know your time is valuable, so let's begin. So as I mentioned a couple of minutes ago, this is our Ask the Moldflow Experts webinar. The topic today is how thin is too thin. This is an important topic in the injection molding industry. A little bit about me, my background's in physics and math. I've been here at CAE Services for a very long time. I'm expert certified. I've trained a lot of certified experts over the years. You may have seen some of the magazine articles I've written, and if you ever attend the Autodesk Moldflow Summit, now called the Advanced Manufacturing Summit, I've been a presenter there a few times too. So I've got a lot of background in Moldflow and you know, a lot to offer as far as the experience that experiences I've seen over the years. So this is a little bit about our company. We were established back in 1988. We have the most expert certified Moldflow engineers in the world. We are an Autodesk partner on the Moldflow side, and we've completed some 25,000 consulting projects over the years, which again points to the experience with these types of parts. So a lot of good background that we have to offer. So why are we here today? So you know the notifications we sent out mentioned lightweighting for EV or electric vehicle parts, becoming a very important topic. You know, it's been an important topic really for a long time in the automotive industry, but you know, it's gaining more and more traction as the years go on here. So EV applications are seeing more lightweighting, but automotive in general has been seeing it for a while. And you can see the chart there. Over the years, what has happened is, you know, the gradual conversion from steel to plastic has taken place to get a lot of the weight out of the car just by the fact that they're switching from steel to plastic. But now we're going the route of reducing the weight of the plastic components themselves. So you can kind of see a leveling out over the last 5 to 10 years of the total number of pounds of plastic in a light vehicle. But I would argue that there are a lot more plastic parts going in there, and they're being lightweighted. So the amount of plastic is leveling out, but the number of plastic parts is increasing. And so it's incumbent upon us as plastics engineers to understand, you know, what the implications of that are. You know, how do we manufacture plastic parts, not just for the electric vehicle industry or automotive in general, but also for other types of parts as well. So what I want you to take away today are these things here. So first of all, in those of you who have been around injection molding for a while, you know, injection molding is a balancing act. You know, whenever you try to push the envelope in one direction, there are always consequences to that. And so I'm going to point some of those things out today. So we're going to understand the benefits of having thinner plastic parts. I think some of those are pretty obvious, but we also want to understand the consequences of having thinner plastic parts. And we're going to show areas where this influences injection molding. So lots of different areas that that it touches on, whether it's filling or warpage or cooling. And then we're going to suggest some potential solutions along the way for each of those areas. So what do we mean by thinner? So a lot of this depends on what type of part you're dealing with. You know, if you're in the automotive industry, a lot of times you're dealing with big parts. So you know, automotive trim, for example, the focus is more on efficiency and cost, right? Yeah, you want to be able to mold parts faster. You want to reduce the amount of plastic you're using and get the cost out of these parts. So, you know, 10 to 15 years ago, 3 to 3.3 millimeter walls were typical for these types of parts. 5 to 10 years ago, started the reduction process to 2.8 to 3.0 millimeters was pretty typical. And now we're seeing a lot more 2.5 millimeter wall parts, for example. So the trend has been coming down, as I mentioned, you know, with the amount of plastic that is in each light vehicle. So again, there's going to be some consequences of getting to these thinner walls. But it's not just automotive that you know, uses thin walls. Medical electronic packaging, they've been using thin walls for quite some time. Their focus isn't so much on efficiency and cost because their parts are so small. This part over here on the right, for example, that's only 1.5 inches long. And there's a membrane in there that's extremely thin, like 0.2 millimeters. So the focus here is more on functionality. You know, anything goes really. It's really what matters to the functionality of the part. You know, in some cases, we're seeing thicknesses on microchips, for example, less than 1/10 of a millimeter. So they need that functionality to make their part work the way they want it to. So we have to figure out the manufacturing solution in terms of how to get it filled, how to make it work. And then, as I said, the benefits of having thinner parts, you know, these are fairly obvious. Less plastic means reduced weight for engine efficiency, for example. Energy consumption, whether it's gas, you know, on a standard combustion engine type automobile, or you know, for a fully electric vehicle, the battery efficiency. And then, of course, converting that battery energy into horsepower for the engine is important. And then, of course, we have reduced manufacturing costs. We have faster cycles. We have reduced plastic costs in general. Okay, but on the opposite side, as I said, plastics injection molding is a balancing act, right? So, you know, there's a danger to going to thinner plastic. And, you know, in some cases, if you're not paying attention to what you're doing, you can get on thin ice with your boss or with your company. I've seen some disasters out there that were the consequence of going to too thin of a part. So thin wall means part quality issues. You could have backfills or non-fills. You could have read-through, meaning sink marks on a show surface, for example. You could have warpage or buckling. You could have reduced part performance. I mean, thinner walls aren't as stiff. They don't hold as much load. You could have increased molded in stress, which could decrease the plastic material properties that you assumed were there when you looked at the material data sheet. And of course, you could, on the opposite side, have increased manufacturing costs. You know, it seems too simple that, you know, reduced amount of plastic will reduce the amount of manufacturing costs from a cycle time standpoint, from a less amount of plastic standpoint. But there are increased manufacturing costs that often go unseen, like larger molding machines. You know, you have a thinner wall, you might have to put this in a larger molding machine to be able to hold the clamp force. You might have a more expensive mold to build, more hot drops, for example. You know, if you've got a valve gated mold, with a bunch of hot drops in it. Every one of those drops is going to cost you, thousands upon thousands of dollars. So it's a balancing act. So our motto here at CA Services is predict, identify, and solve using Moldflow software. So this was a case that we worked on a few years ago that was shaping up to be a bit of a disaster. I took a picture of one of these outside the window of my car one time traveling down the highway, but this is a mud flap on a tractor trailer, and the backstory to this is that some injection molding machines were purchased, millions of dollars invested for these large parts, and the first molds, or the first parts off the mold, were showing a very buckled situation in that top piece there. And we'll get into this a little bit later, but they wanted to have a thinner wall on this top piece, but didn't consider the implications of doing that on the manufacturing side. So the customer is getting ready to pull these molds and send them elsewhere to solve the problem. But it really wasn't a molding problem so much as it was a part design problem. So we leveraged the use of our knowledge in buckling and the Moldflow software to solve this problem, and we'll show that a little bit later. So it's really a part quality issue, and in some previous webinars that I've done, I kind of approached it from a five-pronged standpoint. So all of these things go into determining the part quality, right? We have the mold design, we have the part design, we have the material, process settings, and then, of course, on when we're trying to be predictive of the part quality, the simulation expertise on the Moldflow side is important. So we're gonna get into just almost a random list of things that are involved in the thin wall applications and what we need to pay attention to. So first thing we're going to get into is filling speed. So this is a medical application, and this they call this a cannula. You'll see here in a second that with that thin wall, oftentimes you can get into a situation where you have an air trap. And this is kind of a thick wall versus thin wall deal, where plastic wants to go into the thicker walls, and meanwhile it hesitates as it goes into the thin wall. So what you end up with oftentimes is a backfilling condition, as they were seeing here, and also a knit line situation, which can compromise the integrity of the part. So if they were this particular thing, you see a sharp point on the end, it had to puncture another piece, and if the knit line and the backfilling occur, sometimes that can compromise the integrity of the structural integrity of that little cannula there. So one of the solutions to doing that is looking at your fill speeds. And you can see with a quicker fill speed on the right, we were able to help mitigate that a little bit. But ultimately, a better choice would have been a thicker design. We're here to talk about how to make things thinner, but sometimes, for functionality's sake, you have to find out where you can draw the line. And in this case, a thicker cannula might have been a better solution. But oftentimes we can get through this by changing the process. And in this case, it was a fill speed issue. Here's another case, another medical application. Again, this is a very small part, even though it looks large on the screen. We have thin wall versus thick wall going on here again. There's a membrane in the center of this that needs to be punctured. It's a 0.2 millimeter wall. So standard injection on this was going to be a very difficult thing to do. So if you look at standard injection, you see a major backfilling situation in there. And this would be large potential for a short shot by injecting the way we're injecting here. So we came up with a different solution on this, and this was actually kind of unique in the sense that we're using compression on this. So what we did is we actually pulled back the core to make its starting position thicker, and we kind of iterated on that. We did one with a 0.6 millimeter start position and a 1.2 millimeter start position to allow that material to shoot through the membrane without backfilling or knit lines. And then what you see here, you'll see in a second this core will start to move. So we actually have the ability to simulate that movement of the core, fill it first, and then compress it in a very short period of time so that area doesn't freeze off quickly and end up with that 0.2 millimeter membrane. So very, very unique way to achieve thinner walls. And the total time to do all that, inject and compress, was on the order of 0.6 seconds. So one of the things that you have to pay attention to when you're dealing with thin walls is material degradation. So on this same part here, if we had gone with conventional injection and we were able to fill it, you see the elevated levels of stress there that are caused by the injection process in conjunction with the thinner walls. So thinner walls means a higher amount of molded in stress. And when you have a higher amount of molded in stress, that's telling you that the manufacturing process is affecting the part quality. It's affecting the, again, the assumptions that are made about the material properties when you look at a material data sheet, for example. So this molded in stress can actually reduce the amount of yield stress required to make a part fail in its functionality. So notice the difference here between the conventional injection and the compression solution. So there's, on the same scale, quite a reduction in the amount of molded in stress in that part. It's not just this type of part. You see it in automotive parts as well. You know, the thinner and thinner you get, and especially with more amorphous type materials, you know, the higher that molded in stress goes. And the higher that molded in stress goes, if that part has to hold some sort of a load, you may end up with quicker failure, not just because it's thinner, but also because there's a larger amount of molded in stress there. Okay, so that's thin walls as far as filling patterns is concerned. Now we're going to talk about the number of gates and how it relates to pressure. So here's a bolster part that we worked on, and on the left we have a 3 millimeter wall, and with 3 gates. You know, not the best balance in the world, but you know, it's a workable solution. 14,300 psi to fill that. When we reduce that to 2.5 millimeter wall and using the same gating option, now our pressures are increased up to 17,000. And if we were to push that even further, you know, now you're starting to get up close to the capabilities of the machine. You know, 20 to 25,000 psi is pretty typical for an injection molding machine. Okay. So, but this is one of those cases where with the, that should say 2.5 millimeter wall, with 4 gates, we were able to get it down to 12,000 psi. Okay, so this is where adding a gate, you know, gets you in a more, a larger molding window, but now you've got the consequence of you've got an extra gate, so that's going to cost some additional dollars in your mold design. Not only that, but you have to pay attention to what's going on with clamp force. So with those same 3 situations, you know, we got the 3 millimeter wall with 3 gates, 1,700 tons, 2.5 millimeter wall with 3 gates. Now we're up at 2,400 tons. So let's say you're slating this part to go into a 2,000 ton press. Well, now all of a sudden you reduce the wall thickness so much that you can't mold it in that 2,000 ton press. You have to go with a 2,500 ton press if you're going to stay with the 3 gate situation. But going to the 4 gates, we're able to get it back down to the 1,500, almost 1,600 tons. So clamp force is affected because the pressure is affected. Pressure is affected because of the gating scheme. So all of these things are interconnected, and all of these things are potential problems if you're not able to simulate this ahead of time and see what you're up against. Here's a chart. I did a little DOE on this part. You know, looking at on the x-axis here, 5%, 15, 25, and 35% increases in wall thickness from nominal, and then 25 down to 25% less. So you see from nominal, as you go thinner and thinner, we have an exponential increase in pressure with the thickness. Okay, so it doesn't take long before this pressure starts to get out of hand. Now this is a large, part with a TPO type material, so pressures generally, are fairly manageable. But imagine, a material that's a little harder to fill. That pressure can get out of hand real quick, like polycarbonates, PCABSs, things like that. So exponential increase in pressure with a decrease in thickness is the big message there. On the cooling side of things, we tend to have a linear decrease in temperature with the thickness. So as those thicknesses come down, this is where we see benefits, right? And it tends to come down linearly. And then what I found over the years is about for every degree in temperature that we reduce something, equates to roughly about a second saving in cycle time. So that's how to look at this. So notice when we go down to like a 15% decrease in the wall thickness, we might be saving up to 5, 6, 7 degrees in temperature, which is going to equate to that 7-second cycle improvement. To be more specific on this one, we look directly at some of the temperatures. Now, on that previous plot, that was cavity surface temperature. This is an average temperature, and we tend to look more at average temperatures when we're deciding where to end our cycle. But on the left here, we have a 3.3 millimeter wall. We have a 39 seconds IPC, meaning injection plus packing plus cooling. On the middle one there, we have 2.8 millimeter wall, and that reduced it by 9 seconds. And then on the 2.5 millimeter wall, we're at 25 seconds, just to get everything to the same temperature. So again, this is where simulation comes in. We're able to see what the benefits are of going to the 2.5 millimeter wall. Part design issues. In previous webinars, I've shown that part design or warpage is a very shrinkage related issue, and it's shrinkage related in 2 ways. Number one, we've got pressure issues with the gating, right? So areas with high pressure tend to see low shrinkage, and areas with low pressure tend to see high shrinkage. So our gating scheme matters in terms of how the shrinkage plays out. But not only that, but we've got thickness related shrinkage variation as well. Here's just a simple mock-up of a part that has 2 different thicknesses, and then also an even thinner rib on the top of that thin section there. And you can see what happens here. When I exaggerate things, the thicker section, as you can imagine, tends to shrink more than the thinner section. And then when we put an even thinner rib on top of there, it wants to hold, it shrinks even less and wants to hold its length. So it tries to bend this part in the opposite direction. So you can see why it's often stated that you should maintain as uniform a wall as you possibly can. But this really illustrates how differences in thickness change the shrinkage of your part. And don't forget, when you're cutting steel to typically 1 shrinkage number, when in fact the material shrinks at a bunch of different numbers throughout the part. So we have to be mindful of how the different part thicknesses play in relation to the shrinkage you've selected to cut your steel to. Here's the fascia again, and you can see with the 3.3 millimeter wall, we have higher shrinkage numbers. These are volumetric shrinkage, not linear shrinkage, which you would cut steel to. And then when we reduce to 2.5 millimeter wall, you can see that these shrinkage numbers come down. So in many situations here, so not everywhere, and some of that's because of how the filling pattern plays out. But by and large, the shrinkage is reduced when you reduce your wall thickness. So what may be stated on a data sheet, a material data sheet for shrinkage, may not apply when you change this part design. Those data sheet numbers are generated under very controlled conditions, and you have your test plaques at a certain wall thickness, and those shrinkage numbers are generated from that. So this matters when you start changing the part design. especially the thickness, your shrinkages change, and then your assumptions about what you cut into the steel need to change along with that. I mentioned sink marks earlier. Here's a case where we have a 4mm wall with a boss on it, 2.7mm boss. Reduce that to 3mm, and we start to see a little bit of an increase in the sink mark depth predictions. And then when we go all the way down to a 2mm wall with that same thickness, now you can expect even thicker sink marks. So got to pay attention to all those features that attach to the main wall when you start thinning your part out, especially if it's an appearance part where sink marks are not allowed. So you're going to have to start reducing the thickness of the attached features accordingly. You know, and as we mentioned before, now we start reducing thicknesses. Now we got to start thinking about non-fills, short shots, those kinds of things. You know, maybe performance issues, thinner walls here, you know, may compromise the integrity of that boss, you know, as it attaches to some other feature. Okay, and then the worst case scenario that we see with thinning walls out is buckling. I call it shrinkage gone wild. So the technical definition of buckling is a conversion of in-plane membrane energy to bending energy, usually involving large deformations in the part. Okay, what does that mean? Sounds pretty complicated. Membrane energy is, you know, energy in the plane of a given wall. And that membrane energy is, in plastics, is shrinkage. It's the material trying to shrink, you know, because that's what plastics do. And if those shrinkage levels are high enough with respect to the stiffness of the part, this part can undergo large deflections in the form of buckling. It just kind of springs out of position. Okay, and this is one of these things, areas in mold flow that is not very well understood, I guess. I shouldn't say well understood, but not often used. It's well understood, but it's not often used. You know, standard mold flow, if you're not paying attention to buckling, then you can get some very wrong answers in terms of the predictions for your molded part. So buckling is really important to pay attention to, especially when you're going thinner and thinner. And you can see this on this particular part, mold flow picked it up very well. So what are some of the remedies for buckling? You can stiffen the part by added ribbing. You can create stiffening features like corrugated surfaces, things like that. And one of the things we found is, you know, sometimes it's an increase in thickness. You know, we're all about thinning walls out, but at some point, you have to find the minimum thickness that you can go to before things start buckling. Sometimes it's a change in material. That's a more difficult thing to do. Typically, you know, you're so far along in a project that material is the material that's going to be used, and that's that. But I have seen cases where parts have buckled, and we've changed the material to get rid of that buckling, and that was acceptable. But this is one of those cases where you would have to do this very early on in a project, and this is what we preach all the time, right? Do mold flow early. If you're doing mold flow early, you can catch these problems, and you have a lot more solutions open to you to fix a problem than you do when you're getting ready to cut steel on the mold, for example. So I mentioned that truck part earlier, the tractor trailer. This is how we did it. We thickened it. You know, at first when we mentioned that solution, they said, no way, this is the way we want it designed, and that's that, make it work. Well, we tried stiffening it up by other features. You know, we added ribbing, we did a bunch of different ribbing patterns and so forth. But ultimately, it took thickening that wall to fix the problem. They didn't want this big dimple in the middle of their part. And you know, it's amazing how the simulation was able to convince people to make a solution that worked. You know, they would have gone down the road of pulling these molds, sending them to somebody else, and that molder would have had the same problem. It wasn't a molding issue, it was a part design issue. Then another thing that might be coming into your head here is, should I use windage? We've done webinars on windage before. So for those who are not, don't know what windage is, it's basically biasing the tool steel in the opposite direction of the expected warpage, expecting that warpage to come back to flat. And we talked about, when to use it, using it when tolerances are reasonable. For example, if you have a tolerance of 0.1 millimeter on a bumper fascia, that's a tough sell when it comes to changing your mold with windage to reach that kind of tolerance. It should be used when all other options have been exhausted. When we've changed the gate locations, we've tried some part design changes, we've tried running it in a larger molding machine or changing the cooling or whatever. All of these things, when you can't fix the warpage through all of these other methods, then oftentimes we rely on a windage solution. And that's something that we at CAE here have gotten very good at. But windage and buckling do not mix. So when we get into these buckling situations, this is the reason we don't want to do it. Buckling is inherently unstable. Small changes to anything in this mold or part design or process or whatever lead to large changes to the warpage. Imagine this guy on the tightrope. That's essentially what you're doing when you're in a buckling situation. You're on a tightrope, and any small movement to the right or left is going to produce disaster. It's going to produce a large deflection there for that guy. So so buckling is not a good idea, or windage rather is not a good idea when it comes to buckling. Because windage essentially changes the part shape as it sits in the mold. So if we are going to use windage, we need to stabilize the part first, and we're going to use Moldflow to do that. So as this example shows here, there's still some warpage left in this part, and if we had gotten to this before the mold was built, the thickness change was a relatively easy change to make, but to put windage into a tool after the tool's already built is a much more difficult situation. But if we had gotten to this beforehand, there's still some warpage left in the bottom of this, on the bottom edge of this part here. Luckily, the assembly allowed for that to be okay, but if they needed to correct that, that might have been a windage solution. We stabilized the buckling, but now there's still some warpage left to take care of. So that's the main point with buckling parts, is you got to stabilize the part first before you get to the windage solution. I preach this in just about everything I do, Moldflow wise, but make sure that any materials that you're using are well characterized before they're being simulated on your mold. In this case, we're showing exact same setup in two cases. In one case, we have material without juncture loss data. In the other case, we have it with juncture loss data. And you can see the difference in the pressure predictions, okay? So, and this is just in a standard part. If you go to thin parts, this becomes amplified pretty quickly. Remember, the pressure increases exponentially as you try to reduce wall thickness. So if you're simulating materials that are not well characterized and you're trying to make a decision on whether or not you can mold this thin wall part, you better be very careful with how you substitute materials. Make sure you have good, well characterized materials. And then with the buckling situation as well, these pressures matter when it comes to predicting shrinkage. If you predict pressures well, you predict shrinkage well. If you predict shrinkage well, you predict warpage well. If you predict warpage well, then you're going to detect buckling from time to time, and you want to make sure you got that answer right. So everybody wants me to answer the question, how thin is too thin? And I'm going to give the cop-out answer. How about that? The answer is it depends. And you have to ask these questions. Will it compromise the part functionality? A lot of people doing structural analysis on their parts to make sure if this is a load-bearing part that it's going to still be able to withhold the loads with a thinner part. And understand that when you're doing structural analysis, you're doing it with perfect material properties. You have to understand that when you manufacture a part, the manufacturing process itself affects the mechanical properties of a plastic material. Second question, is it causing backfilling or non-fill issues? We showed a couple of examples where that becomes an issue. You know, if you're not, if you're going too thin and you're molding that alongside of thick walls, you're going to have some backfilling issues sooner or later. So, you know, can we fix this with a gating solution? Can we fix it with a processing solution? You know, with these thin walls, you're inherently going to have a tighter molding window. So the options you have available to you in terms of a process are going to be fewer and fewer when you go thinner and thinner. So you got to know these things ahead of time before you get into it. So, you know, is it causing a backfilling or non-fill issue? Can we process that out, or can we institute a gating solution? Is there too much pressure clamp force that's required to fill this? You know, you don't want to get this to the press and find out you can't fill this part because you don't have enough pressure or clamp force available to you. Will it cause ejection issues? You know, do you have a large part and you know, now it's so thin that you can't eject on it? Will my part buckle? We talked about buckling and what that means to your part. Is my warpage excessive? So how thin is too thin? Good question. And it's a question that everybody's going to wrestle with, but I can tell you unequivocally, the only way you're going to know how thin is too thin is if you simulate this ahead of time. You know, use Moldflow to go thin to win here. So leveraging Moldflow is going to help you avoid the pitfalls of guessing wrong. You know, guessing wrong is going to cost you time and money, and in some cases, and I've seen it happen, you're going to build new molds because of it. And that's a very expensive solution. It's going to help you determine where that line should be drawn and reduce the guesswork, excuse me, the guesswork. And it's going to help you determine solid solutions and one that doesn't involve building a new mold, for example. So in the part design area, we talked about thickening walls, or in some cases, maybe making them more uniform when it's a filling issue. Maybe we need to add ribbing or structural features. Maybe we need to change the process, faster fill, larger molding machine. You know, every case is different. There's not, you know, I get asked all the time, is there a rule of thumb, you know, like the length to thickness ratio in terms of how far we can fill and so forth? Every material, every part design, every mold design, there's millions of combinations out there, and every situation is different. So it's hard to put a rule of thumb on these things because there really isn't any standard rule of thumb for these situations. And of course, if you're going to simulate, you better make sure that the people doing the simulation are experts at it. Make sure they know, you know, that they're going to know when the results are reasonable, when the material data is good, when the mesh is good, know how to move gates, know how to process, know how to change a part design, know how to use windage to fix warpage. All of these things go into determining solutions. So, you know, I mentioned the buckling situation previously. Knowing what that means and how to detect it and what type of mesh to use to do that and so forth to detect buckling before it occurs is really important. So what's new here? Maybe it's not so new anymore, but we are partners with Autodesk. You know, we are resellers of their Moldflow software. We are trainers for Moldflow, and we are mentors for Moldflow. So if you want to become an expert yourself, that's the way to do it, is have someone come alongside you and help train you and teach you and show you the right way to do Moldflow analysis. So we have training, classroom, and online. We have these webinars bi-monthly. So keep your eye out from our newsletters, LinkedIn, email blasts, that kind of thing. We will be doing webinars throughout the year. We have Moldflow office hours, so anytime you just want to sit and talk Moldflow. You can sign up for some Moldflow office hours and any topic, your choice. Be happy to dive deep into any Moldflow subject that you'd like. We have a new website. It's not so new anymore, but visit us at caeservices.com or follow us on LinkedIn. Those are ways to keep in contact with us. Okay, lastly, we have some questions that were submitted ahead of time, so I'm gonna dig into some of those. Somebody asked a question, what are some good gating strategies for long, thin parts? So long, thin parts, as I mentioned before, pressure is a big deal. So the farther, obviously, that the plastic has to flow, the more pressure is going to build up. So, and that gets amplified as we go thinner and thinner. So sometimes, it's important to see, if you're using a hot runner system, for example. Sometimes you can use valve gate sequencing. Sometimes you can run all open. Depends on whether or not knit lines matter to you on a given part. But there's lots of ways to skin that cat, so to speak. And again, every situation is different, but valve gate sequencing is one way to do it, and it really just depends on the situation. Let's see here. So, can the results be accurate for a 4/1000th wall section flowing for a 1/2 inch? They can be. The difficulty is in correlation there. If you're able to, if your question are the pressure predictions going to be correct, so forth, that'd be a very difficult mold to instrument with pressure transducers and so forth to determine whether or not you're able to get the right pressure prediction out of that. But yeah, I mean, we can model anything, right? But the correlation side, need to make sure that that's a well instrumented tool. And then you have the issue. I mean, you're literally filling a blip of plastic, and to control that on an injection molding machine can be very difficult. So sizing the injection molding machine matters. Screw and barrel size, that kind of thing. Okay, general design concepts of a thin wall part design and solutions. Okay, we talked about that. Oh, gates around thin walls. So not sure what necessarily you're getting at on this question, but I suspect it maybe has something to do with sink marks. So oftentimes gates around thin walls can produce a greater likelihood of having sink marks. So there are different strategies for that, maybe gating into tabs, thinner gates, of course, but you have to pay attention to shear rates through the gates as material is entering those areas. You also have to pay attention to gate freeze. If you're going to go with smaller gates, then your gate's going to freeze a little bit quicker, and you're going to reduce the ability to pack the part out. So yeah, there are different things to consider when it comes to gate size and so forth around thin walls. Good question here about how how this affects the quoting stage of a project. It's one of my favorite topics when it comes to Moldflow. And when we talk about doing Moldflow ahead of time, this is one of those times you can do it. You don't have to have a fully developed part design to be using Moldflow. Moldflow is very useful even when you're even 80% complete on a part design. What are you up against when it comes to clamp tonnage, for example? That's the big one. What size molding machine do I have to put this thing into? Hourly rates on molding machines go up pretty quickly when you get to larger and larger molding machines. How is that counterbalanced by, the reduction in cycle time? I've seen some pretty intricate spreadsheets that estimators use to determine piece part price, and all of these things go into it. So yeah, I mean, it's important to know, to really hone in on what you're up against if you want to quote your piece part prices accurately. How is venting in thin wall areas approached? So when you have extremely thin walls, now you're starting to, you know, have the thickness of the wall start to approach, you know, some of the depths of the vents themselves. One thing I should mention is in a standard mold flow analysis, it's assumed that you have perfect venting. Okay, so anywhere air needs to get out, in other words, it does get out. Now, when you get into more advanced mold flow analysis, you can actually put vent locations in there and see the effects of the individual vents on the filling pattern. But you know, typically when you're dealing with venting in thin walled applications, you're typically dealing with faster filling, right? So the material has to get out of those vents faster. In some cases, it's going to be difficult to get that air out of there. So you may need a little bit more venting. If you get to the point where the venting is still not adequate, you can pull a vacuum on the vent. You know, what we here at CAE Services, we have our Moldvac product that pulls a vacuum on the venting design and provides an assist to get that air out quicker. So that's the real issue, is the air's got to get out of there quicker, and you need more venting typically to achieve that with a thin wall part when things get very thin. Next person would like some input on determining appropriate gate and runner sizing and fill speed. Well, we talked about fill speed. Appropriate runner and gate sizing, the way we look at runner and gate sizing is we want to make sure that a couple things are happening. Okay, we want to get the conditions of the material at the gate, you know, to be the right temperature, for example. So in some cases, you can use the runner as a shear heating device to get the material to the temperature you want when it enters the part cavity. We don't want the runner to control the cycle. You know, what's the point of having a thinner wall if your runner's going to control the cycle anyway? So, you know, oftentimes it's going to require a reduction in the runner size, you know, and then now we have not only a thinner wall, but we have a thinner runner, and that thinner runner is going to add some to the pressure. So we have to keep our eye on that. So, so how do we determine that? We simulate it, right? So we have to understand what the implications of going smaller on the runner size is going to be. Next question, what can be done to control the movement of tall standing cores as in thin wall container parts? Well, I think we're talking about core shift here, and this is a very good point. You know, if you have a tall standing core and you're filling, when you thin walls out, the pressure difference from one side of the core to the other is going to be amplified when you have thinner walls. Okay, so you know, we talked about the exponential increase in pressure when we thin walls. Well, not only does it increase the overall pressure to fill a part, but it amplifies pressure variations from one part of the one area of the part to the other. So when you have a tall standing core and it has to fill around that core, that pressure differential can increase, and increased pressure is going to increase the likelihood that that core is going to shift and make it, you know, thinner wall plastic on one side and thicker on the gated side. So that has to be paid attention to as well. And actually, Moldflow has the ability to predict the shifting of cores based on those pressure variations. And the last question here is, what materials are most suitable for thin walling? So, you know, whatever's suitable for lower pressure for thick walling, the same holds for thin walling. So typically your amorphous materials are going to be much more difficult to fill than your polyolefins, for example. The semi-crystalline materials are typically going to require a lot less pressure than your amorphous materials. So, you know, again, you have to take it on a case-by-case basis. And if you're going to use Moldflow to help you determine what's suitable, then, you know, again, make sure you have very well characterized material testing. So, so yeah, so any material is suitable to the extent that you can manufacture it, right? So, if you know, pay attention to all those things I mentioned. Is pressure an issue? Is clamp force an issue? is molded in stress an issue? All of those things can be monitored when we're looking at the simulation. Okay, I think that's a pretty good cross section of questions. I want to say thank you for attending. You know, I always love doing these things, and like I said, there will be more throughout the year. I like getting to know people, you know, that are interested in mold flow analysis. I love training. I just like talking mold flow. So, you know, anytime you guys have a question about any of these webinars or anything mold flow, just feel free to give me a shout. You can call me at the number there. You can email me. We're happy to help. So that's it for today. Look for our next webinar invite in the next couple of months here. So without further ado, we'll say goodbye, and everybody have a good day. Thanks again.